some information about limit theorems for this process. So let us move to the overview of the talk. So first part is on motivation and definitions, and then there is a survey of results. And then there is a part here which is not appearing in the table of contents on references, which is quite extensive, being this school somehow. So we will also go a bit, we will also describe a bit some of the references that could be useful to understand better the paper. Because of time limitations, I don't think I have time to present detailed proofs for all the material I am presenting. So I will mainly give you the some of the main ideas, and then in the end you will find linked to 2 papers that are also available on the archive, so that you can definitely have a look at the papers where all the proofs are presented. So let's go to the motivation for this work. And let me also apologize to those of you who have already seen this presentation. It's not the first time I'm presenting these results, but I hope this is of some interest for people who have not yet seen it, as well as people who have seen it and maybe can get further insights from this presentation. So my first motivation, and the main motivation, came from finance. Suppose you have a sequence of positive random variables with a meaning of intertrade durations, these JIs here, and then the YI is a sequence of random variables with the meaning of tick-by-tick log returns. So just an excursus, like, I don't know how many of you are familiar with regulated equity markets, but essentially in regulated equity markets, trading is asynchronous. They use a mechanism which is called the continuous double auction. And after an initial auction at the opening of the market, there is continuous trading for several hours. So typically markets open 9:30, and then in the afternoon 4:35 they close, and they have also a closing auction after continuous trading. These initial and closing auctions are run with different mechanisms, but in between there is this continuous trading where you can place orders to buy and orders to sell. The order to sell are called asks, and the order to buy are called bids. And usually there is a mismatch in the price because you want to buy at a lower price and you want to sell at a higher price. But occasionally there are transactions. So we are focusing on these transactions or trades, and they are asynchronous. Time scale of these transactions is now below milliseconds, maybe microseconds, because of high frequency trading, even if regulators have now created a set of rules which are not allowing some practice that were used in high frequency trading in the previous years. So you have a trade or a transaction. This is when shares change owner, and they are separated by a time interval which is JI. And then you have, this is the logarithm of the price at which the transaction took place divided by the price, the logarithm of the ratio divided by the price of the previous transaction. This would be a log return, tick by tick. Tick is one execution of a trade here. So you can define, however, these two random walks. This is a random walk of times where these capital Tn are the time instants at which trades occur. So they are also called the epochs in renewal theory, but here we are not assuming necessarily that these JIs are independent and identically distributed random variables. And then this would be the logarithmic price. It's a sum of tick by tick log returns. You can always define a counting process by assuming here, we are assuming that there is no accumulation point and you have finite number of trades up to a certain time, small t, which is counted by this maximum. Of course, if these JIs are exponentially and identically distributed random variables with rate lambda, for instance, this would be a Poisson process with rate lambda. Otherwise, it's some counting process that is not specified. You can then consider the random sum here up to nt. Nt is a random variable. Instead of n, and you get this yt, which is the log price process. Now, it can be interesting to consider rescaling of these variables. Let's say that we multiply the JIs by scaling factor small r, and the yi by a scaling factor a small h. These small r and small h are positive numbers, and we are interested in what happens to this process and also this process when r and h vanish under appropriate scaling of the variables. In fact, you can recognize that, say, for instance, if here you had the Poisson process, here yi is, for instance, a random variable with a finite first moment. So notice that these JIs are positive, but the YIs are not necessarily positive. But suppose that they are symmetric random variables with a finite variance. Then you can recognize that this process here, when you send r to 0 under the scaling that I think h over r square is a constant somehow, then h square over r is a constant, h square over r is a constant, then this object here is converging to standard Brownian motion or to Brownian motion somehow. So that's the general setting. So we are interested in these limits. Why are we interested in these limits and not only working with these random variables? Well, it might happen that these stochastic processes in the limit have nice properties and they are easier to deal with than these ones. And also it's interesting to see if somehow the frequency of these trades becomes higher and higher, what would this process here look at a distance? So what would be its limit? So we enter here in the world of functional limit theorem, but for a lot of transparencies now, we will mainly focus on the counting process NT. Yes, so then we will come back at the end on this continuous time random walk or generalized random walk. So now let me use, we keep these motivations in mind, but now we move to discussing counting processes. In fact, we are going to discuss generalizations of the Poisson process. Here, this transparency is not only for classification, but also to set the notation in the next transparencies. So the standard Poisson process, we denote by this symbol here, where this H subscript stands for homogeneous, and lambda would be the rate of the Poisson process. If you change time in the homogeneous Poisson process with a deterministic function with certain properties, you can get the inhomogeneous Poisson process, which almost behaves as the Poisson process after you remove the change of time. If instead of considering waiting times that are independent and identically distributed and following the exponential distribution, you use a different distribution with infinite mean, and I will give you the example of Mittag-Leffler distributed waiting times. You end up with a process which is a renewal type of renewal, counting process which is of renewal type, which is the fractional homogeneous Poisson process. And our generalization is here and has this notation N alpha. So this transparency, there is the one-point distribution for the homogeneous Poisson process, which is well known to everybody in the audience. And in homogeneous case, as I mentioned, you have an intensity, which is a function from 0 to infinity, and the rate function, which is an integral of the intensity. And the distribution of the increments still follow this Poisson distribution, but with a constant lambda t, lambda multiplied by t, replaced by the rate function in this way. Now I have briefly described these two objects, and now I go to this one, the fractional homogeneous Poisson process. In order to consider the fractional homogeneous Poisson process, you can define it in different ways. So can you still hear me? Because I've seen my internet connection is unstable.
Yes, we can hear you.
Very good. Okay, so
the sound sometimes is a little bit, but we can still hear you.
Okay, so let's hope that the internet connection stays stable. And let me go now to what we have already seen yesterday in the talk by Vassily Kolotoltsev, subordinators. So a subordinator is an increasing or non-decreasing Lévy process. And the alpha stable subordinator is characterized by this Laplace transform. Then you can define the inverse of the alpha stable subordinator by taking the infimum of the times for which the alpha stable subordinator reaches a certain time t, small t. For this inverse alpha stable subordinator, it is possible to derive explicitly a one-point distribution and its probability density. So we call this H alpha, small h alpha. The Laplace transform of this object can be expressed through the three parameters Mittag-Leffler function in this way here. And this, all these results were contained in the talk by Vassily of yesterday. Why do we need this inverse alpha stable subordinator? Because a way of defining, this is just to illustrate the fact that you can compute explicitly, because you have a way of computing the density of this alpha stable subordinator. You can also get the density of the inverse. You can compute it directly, and this is very useful for numerical calculations, but I will not go into details of the numerical calculations now. Now, the fractional homogeneous Poisson process can be seen as a time change of a homogeneous Poisson process with what? With the inverse alpha stable subordinator. Yes, so you can consider this composition of, this is one of the possible definitions of this process, which is useful for us, because we are defining the fractional non-homogeneous Poisson process in the following way. So remember that, as I told you, the non-homogeneous Poisson process can be expressed in this way. So we take lambda equal to 1. This is a homogeneous Poisson process with rate 1. And then you change time with the rate capital lambda of t. And now you take this process and you change time once more with the inverse alpha stable subordinator. And then you have essentially these two time changes. First, you change the internal time with the inverse stable subordinator, then you time change with the rate of the non-homogeneous process, and then you apply to this function, to this function, the Poisson process of rate 1. So this is the definition of our process. You can see here why this is one possible definition, because it would be legitimate to invert these two time changes, and you still get a process that some other authors have studied after we introduced this one. And it is a process that it exists and has nice properties as well. But yes, we were interested in this one. Okay, so in particular, we were interested in characterizing this process through limit theorems. So it is possible to find something on the one-dimensional distributions for this process, but I'm not, because of time limitations, I'm not presenting this result, I guess, here. But let me focus for a second on limit theorems. So you're probably aware that there are at least 12 equivalent definitions of the Poisson process. But the two main textbook, I mean, there are three main textbook-like definitions. So if we go back here, maybe here, one is Poisson process as a renewal process, which can be generalized, of course, where these JIs are independent and identically distributed exponential random variables. And then the Poisson process is defined like that. Second definition is in terms of the rate or intensity capital lambda or small lambda, depending. And the behavior in a short time interval of the counting process. And the third one is as a Lévy process. So it's in fact the only pure jump Lévy process that is all Markovian, as far as I can tell you. But here you have further characterizations in terms of its compensator. The compensator of the Poisson process is just its mean, lambda t, which means that the difference between the Poisson process and lambda t, and lambda ht minus lambda t, is a martingale. And this is another way of defining it. It's called Watanabe characterization somehow. And now you have a one-dimensional central limit theorem for the Poisson process, which is represented here. If you take this martingale and you divide it by the square root of lambda t, then this is converging in distribution to a standard normal random variable. There is then a functional central limit theorem where you have convergence in this Skorohod space And with respect to one of the particular topologies of the Skorohod space, which is called the J1 topology. And this is converging in this topology, this quantity here. So again, is the martingale, but this time divided by the square root of lambda. It is converging to standard Brownian motion. And then you have another functional limit, which is a functional scaling limit. You take the Poisson process, you multiply the time by a constant c, sorry, you divide by c, you let c diverge to infinity. In this case, you have convergence to the mean of this object here. I mean, this is what you can see when you are plotting the Monte Carlo simulation of a Poisson process for a long time t. You would see that it is indistinguishable from this straight line here with slope lambda. Now, we have these results, nice results for the Poisson process. What can be done for this process here? Well, let's start with the easiest thing, which is this functional central limit theorem. We can prove very easily that if you take as a compensator lambda multiplied by y alpha of t, you remove it from the fractional non-homogeneous Poisson process and you divide by the square root of lambda, then you still have convergence, but this time the functional convergence is no longer to the standard Brownian motion, but to standard Brownian motion time change with the inverse stable subordinator. This is easy to prove, and you can use essentially continuous mapping theorem here. The other result is the one-dimensional central limit theorem. Yes, this one-dimensional central limit theorem can also be extended, but it's a bit more complicated. You have to be careful and consider a specific filtration, which is given by a combination of the natural filtration of the counting process and also you assume that you are knowing everything about the compensator since the beginning of the times. So this is somehow what you have to assume in order to prove this. The filtration is defined here. So you take the sigma algebra generated by the counting process itself, so it's natural filtration, and then the sigma algebra generated by y alpha of t, but from t starting from 0. So you assume you know the behavior of this object since the beginning, and then you use this filtration. If you do that, then this object here, where you remove the time change and you divide by the square root of the time change, still converges to standard Gaussian random variable for capital T going to infinity. The proof is, again, not very complicated because you can, essentially, this is a corollary of a theorem that you can find in the book on point processes by Daly and Vere Jones. But it is interesting because in the more applied literature, some physicists were using a different scaling, and they were not obtaining a normal random variable. On the contrary, it is possible to obtain a normal random variables by appropriately rescaling your process. This is illustrated by these Monte Carlo simulations for our process. So this is essentially the case in which alpha is 0, 1. You see here after 10 to the 12 steps somehow, so time 10 to the 12, you are not still there, but you are very close to a standard normal distribution. If alpha is 0.9, on the contrary, you reach the standard normal distribution at time step 20. So this is something which is interesting to see also. Usually when you are considering these convergences, if alpha is closer to 1, the behavior of these fractional processes, fractional counting processes, is nicer. Yeah, this is another interesting point. So what happens, in fact, I was just mentioning it now, if alpha converges to 1. If alpha converges to 1, you can use the continuous mapping theorem, given that y alpha of t is converging to the deterministic function t, to prove that essentially the fractional non-homogeneous Poisson process is just converging to the corresponding non-homogeneous Poisson process. I mean, in the paper on limit theorems, we did this explicitly. I mean, this is intuitive, but in order to prove it rigorously, you need some discussion of Laplace transforms. And finally, the big piece is this functional scaling limit, which seems trivial in the case of the Poisson process, that it behaves like the mean, because, I mean, the Poisson process has a variance, actually a standard deviation divided by the mean, which converges to 0. So if you consider for a large time, so if you consider large time behavior, it is clear that the fluctuations around the mean are becoming relatively smaller and smaller. Now, in our case, it's not so easy, but you have a similar behavior. So first of all, we consider one-dimensional limit. This is a one-dimensional limit that for lambda equal to the identity was also described by I think Trinh and co-workers. So we have to assume that the capital lambda, the function capital lambda, is of regular variation. So it has this behavior for t to infinity. If this is the case, then the ratio between n alpha of t, our process, our fractional homogeneous Poisson process, and lambda of t to the alpha for t to infinity is converging in distribution to this random variable here. Y alpha is of t is the inverse stable subordinator. This is the inverse stable subordinator computed in 1. You have here two indices. This is an index between 0 and 1, and this is a positive index. Yes, so Trinh and co-workers were considering the case beta equal to 1, where you have essentially here the identity. And so you have the ratio of the fractional homogeneous Poisson process with t to the alpha. And they noticed that it is not converging to a normal random variables, but rather to y alpha of 1. But this result is more general somehow, and we will illustrate this with Monte Carlo simulations later. The nice thing is that this result can be extended to processes. So again, in the same hypothesis that you have a regular varying function, capital lambda, this rate, then the ratio between n alpha of t tau divided by lambda t alpha for t to infinity converges to the process of y alpha of tau to the beta, for, of course, for positive time tau. That's a nice result. So to prove this, we use the standard strategy. The first one is to prove the convergence of finite dimensional distributions for this process, but it is in fact using a theorem in Grandel sufficient to show the convergence of this process to this process. So this is simplifying somehow our proof. So we have to study the finite dimensional distributions of this process here. And the other thing, we need a sort of compactness, which is called tightness, which is for free, exploiting here a theorem in Jacob and Shiryaev, because the applications here, the mappings, are continuous and non-decreasing. And so we are left with the proof of the convergence of the finite dimensional distribution. So here I am considering this finite dimensional distribution. So this is the representation of this vector of random variables for times tau 1 to up to tau n. And now we are interested in the behavior of the probabilities of these objects here. It is possible to show that the characteristic function of this has this shape, and because of the property of variation, this simplifies to this form. Then we can compute this expectation explicitly, because we know this H alpha. And by dominated convergence, we conclude that the limit for t to infinity of the characteristic function of the vector is given by this form here, which is the characteristic function of the limiting process. Remember, you have y alpha tau to the beta, and this is what we wanted to prove here. And this is an illustration not of this theorem, but of this theorem here, which generalized the result of Uchaiting. So the one, sorry, this one on the random variable, the one that we were discussing before. Again, by running Monte Carlo simulations, you see that here for alpha 0,9, we can prove the convergence to y of 0,9 at time 1 to the power 0,7, which is, I don't know if you can see this red line here, would be the theoretical limit, which was nice when we saw this result. As I promised, just as a conclusion, we were also working on continuous time random walks. Let me quickly go back to the beginning. We're interested in the scaling behavior of sums of this kind, yes? And now we are able to say something on sums of this kind when this counting process here is our non-homogeneous fractional Poisson process, and these yi's are random variables with certain properties that we are going to describe in this theorem that I am now going to state. So you can see it. So you have the fractional non-homogeneous Poisson process, and you assume that capital lambda is regularly varying with an index beta. Then you consider now here independent and identically distributed random variables that are also independent from the fractional non-homogeneous Poisson process. Now you assume that the law of x1 is in the domain of attraction of a stable law. And here I tell you what this means. Essentially, it means that you have some either limiting Gaussian distribution or a limiting alpha stable distribution. And then the fractional compound Poisson process Z of nt, which is the time changed sum of these random variables, but time changed with the fractional non-homogeneous Poisson process, has the following limit. You take Cn being a sequence where you take lambda of n, and the sequence would be the integer part of lambda n of n, and the sequence would be the one that you have here for the stable law. You consider the process computed in n multiplied by t, and you let n to infinity. This is converging in another Scorot topology, which is M1 to what? To the stable process time changed with the process y alpha t to the beta, which is the one that we were studying in the previous part of the. This is a nice result, and it's essentially a corollary of a result by Anscombe and other authors, among whom Mogyorodi, Csörgő, and Fischler. Sorry if there is someone from Hungary for my not very good pronunciation of Hungarian. This is a one-dimensional result. And sorry, it's not a one-dimensional result, but in the one-dimensional case, we do not need the independence between nt and xy. This is a corollary of a paper by Anscombe of 1952. And then there are these results that these sequence xi can also be mixing. So you have, in one-dimensional case, more general results. I think this is it. I would like to mention that this is joint work with Nikolai Leonenko from Cardiff, who will present in the next day talk on multifractality. And Mylan Trinh is highlighted because this was essentially a part of her PhD thesis. And she was working with me and other co-workers when she was PhD student at Sussex, and now she is working at UBS in Zurich. And these are the two papers. So you can find the transparencies in already in the site of the lectures, the site that Jelena put kindly online. So you can just copy and paste this archive and you will find this paper. Or you can go to the site of Statistics and Probability Letters if you have access to see the full paper. This paper here is the first of the series where we introduce the process and we give a first characterization. In particular, we derive some results on the one-dimensional distribution, one point or one-dimensional distribution for the process. The limit theorems are discussed in a paper which was recently published in the Journal of Applied Probability. And again, you can find it in the archive. but of course, before coming back to this transparency, it is interesting to see a little bit more the literature. So first of all, in our work, we were using a lot the book by Bremont on point processes and queues, where he discusses point processes from the martingale point of view. But we were also using the Bible by Daly and Vera Jones, an introduction to the theory of point processes. This is a 2-volume book where you can find almost everything on point processes up to 2008. And then there is this famous paper by Anscombe, which is somehow, I mean, I call it famous because we used it a lot, but it has been neglected for a long time. These are the results on the mixing sequence. Here you can find the definition of Cox processes presented by Cox himself. Yes, so on this theory of functional convergence, one of the references is the book by Jacob and Shilyaev. Somebody told me that when they came out with this book, they killed somehow the field. I do not really believe it. It's a very nice book, but and a lot of results are inside that book, but there are many other things that have to be studied. So just to mention the fact that some of you may be probably aware that so I was mentioning this space. Let me tell you something more about this. Yeah, this one. This space, capital D of 0 infinity. So this is a Skorohod space. What is this? This is a space of Cadlag functions. What are Cadlag functions? The Cadlag functions are right continuous functions with left limits. In French, I think continu à droite et limite à gauche. And then you can define several distances in this space. And one for the J1 topology, it works like that. So you take the absolute value of the difference between your function and a linear mapping, which is increasing between your function and the interval you are interested in. In this case, it would be 0 infinity. And then you sum to this the distance between the time and this time transformation, again, the absolute value. And then you consider for both of these two sums the supremum or the maximum, depending on whether you are in a compact set or the properties of the functions, etc. But let's say the supremum. And then you take the infimum over all these monotone transformations, and that gives you a distance in this space. This distance is such that the Skorohod space is not complete with respect to this distance, in the sense that you can show that there exists that there exist sequences of functions in the Skorohod space that do not converge to an element of the Skorohod space. So, for instance, a colleague of mine here at Vladimir recently published a nice paper in which he was explicitly characterizing the completion of the Skorohod space. So which functions you have to add to the Skorohod space in order to make it complete. And this was to the best of my knowledge, not present in the literature, because, I mean, the completion were done in several books, papers, etc., in a very abstract, sorry for that. Now, let me see. Yes, this is the paper by Watanabe on the characterization of Markov processes and so on. So Cox processes are also defined in this paper by Kingman. This is Mogio Rudi paper that I was mentioning before in the limit theorem. This is the book of which devoted mainly to Qs. This is the characterization by Janros of counting processes. And yes, so this is an extensive bibliography. And I think I could stop here, thanking everybody for their attention. I do not see questions in the chat so far. So if there are questions or comments, please feel free to ask me. I will be around in any case in the next days, in the morning and in the afternoon. You can also send me emails or whatever if you do not have specific questions now. Oh, thank you. So
yeah, thank you, Enrico, for the wonderful talk. And I have, yes, I have the first question. It's from Joseph Lorenzi, and he says, I don't know if you, well, okay. In the Q&A part, that Morgorodi's name came off in a perfect pronunciation.
Ah, thank you very much.
Okay, so do we have any other questions? Questions? Well, then, I probably will ask a very general question. In the beginning of your talk, you mentioned that part of the motivation for the creation of those processes, for considering those processes, was coming from high frequency trading.
Yes, was coming from a high define.
Yeah, and do you know?
Can you hear me?
Yeah, well, there was a lag. Yeah, so yes, so it was coming. Yes, and and Adam Hesse is asking, how do we apply these ideas? What is it? In real life situation and trading. So I'm just, yes, I'm asking, do you know of any particular applications of those processes in high frequency trading, or?
Yes, so I have seen some papers by some colleagues on option pricing, where they are considering options close to maturity, maybe 1 day or 2 days before maturity. And so they are using some of these ideas in order to try and price them. Myself, I tried to write a paper on high frequency option pricing, but to be fair, I mean, option pricing close to maturity is an interesting point. I was, on the contrary, considering intraday options, which are non-existing instruments, or, I mean, they could exist in betting houses, perhaps, where you open a transaction, and you open a position during the trading day and you close it before the trading day. And of course, not this particular modeling, but these ideas that I gave you at the beginning could be used for pricing in that case. Of course, when we were considering this fractional non-homogeneous Poisson process, we didn't consider, for instance, estimates and so on. But also you have to be aware that both these waiting times here and these log returns are not independent and identically distributed. Okay, with this process you go out, but there might be here, it might be better to model this process and this process using perhaps self-exciting processes like Hawkes processes. And here maybe people would like to use Garch kind or other kind of processes to simulate these time series. And then here there is, of course, with Monte Carlo simulations, you can deal with this process very easily and you can try to price options. Intraday or close to maturity, the advantage is that the interest rate should not be a limiting factor. So you can assume that it is 0, for instance. So, but then I don't know, because what people, I think I have a friend working in high frequency finance, but every time he tells me, but we do very simple things, but I cannot tell you exactly what we are doing. So it's
okay. So if they're using it, they wouldn't tell you anyway.
Yes, yes. Of course, just if you're interested in modeling, you could consider this also as a model for diffusion in random media, where you have centers where you can stay for a long time and then you jump very quickly to another position. So this would be a non-physical, in the sense that the jumps are instantaneous. So you would have jumps with infinite velocity, a non-physical approximation to a physical process. Therefore, this limit here would be the limiting process. Maybe the equations for the 1-point probability of this process, which have been discussed also yesterday by Vasily Kolokoltsov, and maybe we will have further discussion in the future talks by the speakers, Josef Lörinci and Nikolai Leonenko, and also you, I don't know. But then this would be essentially a generalization of the Fokker-Planck equation. And there are a lot of work in this direction in the physics literature and also in the biological literature, because of course, I mean, biological matter is usually quite disordered, and so models like these ones could have been, could be used there. Yes, so I mean, I was focusing on finance in this discussion because this was my main motivation to start this work.
Well, yes, thank you very much for your very good answer. Do we have any other questions? I saw that Professor Mainardi had a question, isn't right? No? Okay. Any other questions? No? Well, if not, let us say, yes. If not, let us thanks Enrico again.
Thank you very much for coming, and see you around in the next days.
Yeah, thank you very much. It's our first experience in online talks, so I hope you enjoyed it. And